Hey guys, so today we're going to look at day 2 of 2.2. Last class we took a look at operations of functions, and we realized that we could take two functions and we could add them and subtract them, multiply them and divide them. Now what you need to understand is when you do that, you're creating a new function. And just like day 1 when we talked about functions, if we're creating functions, that function could have domain restrictions that we need to pay attention to. So we didn't do this last class, but we're going to do it this class. So we're going to do the same thing that we started. I'm going to take two functions and I'm going to add those together to create a new function. And I'm going to subtract and I'm going to multiply and I'm going to divide. But then we're going to stop and we're going to take a look at what the domain of that new function would be. Now in general, here's what happens. The domain of our new function is going to consist of all the x's that are in the domain of both of these. So if this is all real numbers and this is all real numbers, then I promise that our new function will have a domain of all real numbers. If function f has a restriction like x cannot equal 2, then our new function will have that same restriction that x cannot equal 2. Okay, everything else is fine. If f has a restriction like x cannot equal 2 and g has a restriction like x cannot equal 3, then both of those restrictions will then be restrictions on our new function that we're creating. So that's the general rule. Now, for dividing, there's going to be an added little element. So the domain of this new function that you get when you divide is going to be all the x's that are in the domains of both f of x and g of x. But we also have to make sure, since we're dividing by this function g, that g doesn't equal 0. So we talked about that on day 1, where if you have a fraction, you got to make sure the denominator does not equal 0. So when we do the division, not these, but when we do the division, we also have to pay attention to that. Okay? So first example, I've got two functions, f of x and g of x, and I want to do these 4 operations. So I want to find f plus g of x. So I'm going to add these two functions together. Well, there's no like terms to combine, so all we can really do is just write 2x squared plus x minus 1. Okay, we're just going to combine them into one function, and then we're going to find the domain of that. Well, again, the domain of function f is all real numbers, because there's no fractions or no radicals. The domain of function g is all real numbers, because there's no fractions and no radicals. And again, when we add those together, we don't have any fractions or any radicals. So the domain of our new function is all real numbers. I have a feeling that this is also going to be all real numbers, because that's what the rule says. When you're subtracting, the domain is just the same as those two put together. So let's see. If I subtract g from f, I'm going to get x minus 1 and then minus 2x squared. You can leave that. If you want to write it in descending order and put the negative 2x squared first and then put plus x minus 1, I'm fine with that. But again, we don't have any fractions, no radicals, so there's no cause for concern. So our domain is going to be all real numbers. F times g of x. Okay, so we're going to multiply these two together. So for this, we're just going to distribute. The 2x squared is going to multiply the x. So that's going to be 2x cubed. And then the 2x squared is going to multiply the 1. So we're going to get minus 2x squared. But again, nothing fancy has been created. So our domain is going to be all real numbers. This is the only one that's going to be different. So on this one, I've got function f being divided by function g. So function f, x minus 1, function g, 2x squared, and that's it. That's all I can do with that. But now I have an issue with the domain. Now I have a fraction, so I need to make sure that I don't plug in anything that would give me a 0 in the denominator. And if you look at this, the only thing that would do that would actually be a 0. So if you plug a 0 in, it's going to make this whole denominator 0, and then the world's going to implode on us. So the domain is going to be all real numbers except x cannot equal 0. All right, example 2. Now, I've got f of x and I've got g of x. These are a little trickier looking. Okay, they got some fractions going on here. For these, all we're going to do is we're going to multiply the two, and then we're going to figure the domain of that new function that we create, and we're going to divide the two, and we're going to see what the domain is of that new function. So again, if you just take a look at these, both of these are fractions, so they're going to have some domain restrictions. For this one, the domain would be x cannot equal -2. That would make that one kind of blow up on us. And this one, x cannot equal +1. 1 minus 1 is 0, and we can't have that in the denominator. All right, let's see what happens when we multiply these two. Now, when I take 1 over x plus 2 and multiply it times x over x minus 1, when you multiply fractions, you just go straight across. So 1 times x is x, and then x plus 2 times x minus 1 is, well, normally we would FOIL that out, but I'm just going to rewrite those as being multiplied together in the denominator so that you can see something. Okay, I'm going to write this as x plus 2 over x minus 1, just like that, or times x minus 1. Now, that's my new function. If I FOILed it out, that'd be fine, but there's a reason I'm leaving it like this. Because now you can easily look at the denominator and see what our issues are going to be. I've got two binomials. If either one of these becomes 0, then it's going to wipe out the whole denominator and make the whole denominator 0. So x cannot equal -2 and cannot equal 1, which our rule tells you should have been the answer. Okay, when you multiply two functions, your new domain restrictions are just going to be these two put together. Okay, so it's a combination of both. Let's look at B. B says, what is f divided by g? Okay, so I've got function f, which is 1 over x plus 2, and I'm dividing it by function g, which is x over x minus 1. Now, to divide by a fraction, you actually multiply by that fraction's reciprocal. So let's see if we can simplify by doing that. So I'm going to flip this fraction, and now I'm going to multiply. Well, looks like there's not a whole lot happening. 1 times x minus 1 is x minus 1, and then x plus 2 times x is going to be like x squared plus 2x. And that doesn't really simplify, so that's our answer. Okay, so this is our new function. Now, what is the domain of this new function? Well, if you look at the denominator, I have an x, and I also have an x plus 2. That's what multiplied together to get this. So x cannot equal 0. 0 would wipe this whole thing out and give me a 0 in the denominator. -2 should also be an issue because -2 squared is 4, and then this would give you a -4, so that's not going to be good. Okay, but we also have to look at one more thing. We need to go back to the original function g. Remember, we're dividing by function g. So if there's any input value that would make function g be an issue, like +1, we have to include that as well. So anything, or in this case, 1, yeah, 1 should be an issue anyway. So plugging a 1 into our original function was a restriction, so that's going to be a restriction in our final answer. It doesn't look like it is. It doesn't appear when you look at this to be an issue, but it is. Okay, anything that would mess up your original function, we have to exclude it from our new function, even if it looks like it's not a problem. If you plug a 1 in, it looks like you're fine. 1 minus 1 is 0, but the 0 is in the numerator, and then 1 plus 2. It looks fine, but it's not. Okay, so anything that was an original restriction is going to be a restriction in our new answer. Okay? All right. Now, one thing we didn't do. I introduced composite functions to you, but we didn't create composite functions. Just like we can create a new function called f times g of x, I can create a new function called f of g of x. And it simply, in this case, f of g. It simply is doing this. F of g. We are going to take function g and we're going to place it inside of function f. So this is something we did on day 1. we're going to put an expression into a function. So that x is going to get replaced with this whole expression. So 4, and then instead of x, we're going to have 2x squared plus 3, and then we're going to have plus 1 on the end. So realize, all I did, I replaced the x, I put this expression into that function right there. And now we need to simplify that. So 8x squared plus 12, and then plus 1 on the end. Oh, so 8x squared plus 13. That's our final answer. Okay? What about g of f? What do you get when you do g of f? Well, this means we're putting function f into function g. So we're doing this. We're going to place this function where that x is. So instead of 2x squared, we're going to have 2 4x plus 1 squared, and then plus 3. So this is function g, 2x squared plus 3, with the x replaced with that function. And then we're going to simplify that. We're going to open things up. So FOIL the 4x plus 1. That's going to give you 16x squared. And then it should give you a 4x times 1 times another 4x times 1. So you should end up with 8x. And then a plus 1 on the end. And then plus 3. I can distribute the 2 in. So 32x squared plus 16x plus 2 plus 3. And then I can combine like terms. So 32x squared plus 16x plus 5. All right, so this is a new function. It is function g of f. Okay, and it does what that composition does. If I asked you, for example, what is f, or in this case, g of f of 1. Okay, I could plug a 1 into function f, do that math, and then I could plug that answer into function g and do that math, which is what we did last class. Or I could just put a 1 into this function and get 32 plus 16 plus 5 and be done, because this function does that composition for us. Okay, so that's what we've created. But again, we've created a new function. And whenever you create a new function, there could be some domain restrictions you need to be concerned with. And that's what we're going to take a look at in this bottom section. Okay, so if you look at both of these, it looks like these would be all real numbers. There's no fractions, there's no radicals. But here's what the actual rule is. To find the domain of a composite function, you create the composite function. Okay, so we're going to put function g into function f, and we're going to simplify it just like we did. We're then going to look at the domain of that thing that we created. So like up here, we're going to look at this and go, oh, that's all real numbers. But we're also going to go back and we're going to look at the domain of the original function g before it got placed into function f. Because if there's any restriction, if there's anything that would make this function g, explode on us before we ever get started, we have to restrict that as well. And again, it may not be obvious when you look at your final answer. When you look at your composition, it may be like, oh, it's all real numbers, we're fine. But if you go back and look at g, you may be like, ooh, wait a minute. If I plug this number into this, it's going to blow up function g before I ever get a chance to put it into function f. So that's the thing we're going to look at when it comes to finding the domain of a composition. All right, so let's take a look at how this works. So I want to find f of g of x given f of x and g of x. Okay, so f of g means we're going to plug function g into function f. So here's my function f. I've only got one x, but that x is where we're going to plug in function g. All right, so f of g of x is going to look like this. 1 over, and then 4 over x plus 4. That's our new function. Now, it's not very pretty. We could probably simplify that a little bit. Whenever we have, and we're going to talk about this later, Whenever you have what are called compound fractions, so you have like fractions inside of your fractions, it's usually what you want to do is you want to make that x disappear. So if I multiply everything by x, okay, so I multiply the top, and all I'm doing is simplifying right now. If I multiply the top by x and the bottom by x, I'm going to get an x on top, and then I'm going to distribute. That x and that x are going to cancel, giving me a 4. That x and that 4 are going to multiply, giving me a 4x. Okay, and then that's really it. That's my new function, x over 4 plus 4x. Okay, so what is the domain of this new function that we created? Well, it's got a fraction, so it's got a denominator, and so we need to make sure that that denominator, 4 plus 4x, does not equal 0. Well, if I solve this, I'm going to move the 4 over, so 4x cannot equal negative 4, so x cannot equal negative 1. So that's our domain restriction, but that's not our only domain restriction. Okay? Plugging a negative 1 into this new function we created would make this a negative 4, and 4 minus 4 is going to give us a 0. But we also need to go back to function g, okay? And this is the part that a lot of people forget. We need to look at the original function that got plugged into this function. And we need to say, wait a minute, did this have any domain restrictions? And the answer is yes. X cannot equal 0. So we also need to get rid of 0. Even though it doesn't look like it would be an issue with this new function we created, it is. It would blow up function g before we ever had a chance to put it into function f. So that is a second domain restriction that a lot of people will forget about. Okay, so that's our answer on that one. Now, look at the next one. Next example. This one says find g of f. Okay, so remember the order. G of f means we are plugging function f into function g. So that function is going to get put right there. So g of f is going to be 2 over, and then we're going to replace the x with this whole function, the square root of x minus 1. All right, so this obviously is going to, so that's our answer. That's our composite function, but now we need to find the domain of that composite function. Well, the domain is going to be such that this expression, x minus 1, has to be greater than 0. Because we're in the denominator, we need to get rid of the or equal to option, so greater than 0. So we're going to move the 1 over, and we're going to get x greater than 1. That's our domain. X can be any number in the world bigger than 1. But we're also going to go back and look at our original function f. So let's take a look at function f. The domain, so I'm just kind of going off to the side here. The domain of f would be this. X minus 1 has to be greater than or equal to 0. So I'm going to move the 1 over, and I'm going to get this. Oops. I'm going to get this. All right, so here's the domain of the original function. X can be greater than or equal to 1. This is the domain of the new function that says x is greater than 1. So these seem to be conflicting a little bit with each other. So we have to choose which one of these is correct. So this one says that x can only be a number bigger than 1, and this says x can be a number bigger than 1 or equal to 1. Here's the rule. When you have a situation like this, you have to go with like the more restrictive domain. Okay, so like if your mom says be home by 10 and your dad says be home by 11, you actually need to be home by 10. Okay, because if you're home by 11, you're going to get in trouble with mom. So you have to go with the more strict domain restrictions. So this will be the domain of that composite function. So you need to be able to make a composite function, so make sure you're paying attention to which function is getting placed into the other one, and then you need to look at that new function you made and figure out what restrictions it may have, and then you have to look at the one that got placed into the other one. So notice on this one, we never looked at function g. Okay, we looked at our new function and we looked at the function that was getting placed into, because that's the function we use first, and if we blow this function up, we'll never get a chance to put it into this function. Again, over here, we never looked at f. F has a restriction that x could not equal -4, but guess what? X can equal -4 in this composition, because that -4 gets placed into G first, and then that answer gets plugged into F. So don't look at that function, look at the first function that got placed into the other one, and look at the new one you made. Okay? Take a look at your worksheet, and let me know if you have any trouble with this.